Hi class, welcome to exercise 2b, where we're going to be working with congruent triangles. In example 3, we'll be proving congruence in triangles. And your pre-learning for this example will be questions 1 and 2 in the new book and question 3 in the old book. Then in example 4, we'll be using congruence in proof. And your pre-learning for this is questions 5 in the new book and question 6 in the old book. We're going to talk about similar shapes later in this unit, and I'm guessing you've heard that before. But in this lesson, we're learning about congruence, and this is a much stricter definition. Understanding congruent triangles will help us with other geometrical shapes, so listen up. Two triangles are congruent when they have a corresponding side which is the same length for each side. There is also a corresponding angle that is the same size for all angles. So these two congruent triangles are essentially the same triangle. It might have been flipped, rotated, translated, which means moved up and down or left and right, so long as all of the side lengths and angles have a corresponding angle and side that is the same. When we say the triangle ABC is congruent to the triangle DEF, we use these symbols in maths. The triangle shapes obviously mean that the 3 points next to this triangle symbol form a triangle with the straight lines between these points. And the 3-line equal sign is like saying a different type of equals, but not as weak as the approximate symbol. So let's have a play with some of these triangle thingies in GeoGebra. Okay, here's a triangle that I can create by moving these 2 points around. Now by pushing this button, I can reflect it to the left. This button allows me to reflect it down. Notice that we've got the exact same triangle despite these reflections. Now I can create one that is reflected about both axes. By moving these sliders, I can move it left and right, and up and down. And I can move this slider to make them all rotate. They look a little like bow ties, don't they? Try the veal. Throughout all of these movements, we still had the same triangles that were congruent to each other. Their side lengths and angles were the same. So let's move on to the next object that I've built. So you can see that I can change the length of the line between these points, and I can also move them around to change the angles. Now if I leave them all at this exact length, you'll see that there's only one possible triangle that I can put together. This means that if another triangle has the same 3 side lengths, then we'll have the same triangle. This includes the mirror image of this triangle. Because it has the same side lengths, we'll end up with the same corresponding angles, therefore it's still congruent. The only possible difference is if I put it in a different location or rotated it. This means that checking that all 3 sides are the same will tell us that the triangles are also congruent. When we write these rules back down in OneNote, we'll call this one SSS, which means all 3 sides are the same. Now if we focus on 2 side lengths, this is KL and this is LM. And just to prove my point, I'm going to mark in the angle and change their lengths. Now if we leave KL and LM to be exactly the same and keep the same angle between them, you'll know that there's only one possible line that completes the triangle. This should be very obvious after linear graphs because there's only one line that passes between 2 points, and there should only be one distance between 2 points. So this means if we have 2 side lengths that are the same, and the same angle between them, then we'll basically have the same triangle. Even if it's rotated or translated, it's still congruent. So when we write down the rules back in OneNote, we'll call this SAS, which means side, angle, side are the same. Finally, let's look at the third object I've created. Here these 2 blue points are called O and P, and moving them around makes a segment of different lengths. I can control the 2 angles that are marked in by moving these sliders. So the lines other than OP, which we can call PR or OR, meet at this intersection point R. You can see that a triangle is formed by OP with the segments PR and OR. And there's only one possible triangle that is formed by this length of OP and the 2 particular angles. By moving O and P, you can see that the length of OR and PR with these 2 angles will also dictate what the length of all the other sides are in the triangle. Therefore, if we know what the two corresponding angles are and one side length, there is only one possible triangle. So any triangles with two corresponding angles and one corresponding side length are congruent. When we write down these rules back in OneNote, we'll call this rule AAS, which means angle, angle, side are the same. Personally, I think angle, side, angle would be far more appropriate for school. Either way, let's head back to the OneNote and write these rules down so we can apply them in the examples. Okay, seeing this is the first new lesson for you in this unit, let's define all of the rules, starting with some definitions that aren't totally about triangles. If we have 4 points A, B, C, and D, if the lines A, B, and C, D are parallel, let me draw that. We write that with this notation. And if A, B, and C, D are perpendicular, and let me draw that, rewrite that with this notation. Alright, and now let's write the test for congruence we discovered in GeoGebra and one more. The triangle ABC is congruent to DEF if 1. They both have corresponding sides that are the same. And we call that rule SSS. And let me draw a picture of that. With this triangle being ABC and this one being DEF. This side length corresponding to this side length, and this side length corresponding to this side length, and this side length corresponding to this side length. With all three sides being the same, we have a congruent triangle. Okay, rule 2 is when two corresponding sides and the angle between them is the same. This is called SAS. And let me attempt to draw these triangles freehand. This one's ABC, this one's DEF. And these two corresponding sides are the same, and the angle between them is the same. So any two triangles satisfying these rules are congruent. Rule 3 is when we have two corresponding angles that are equal, and the same side in relation to the angles is equal. And this is called AAS. See, I told you angle, side, angle would have been more appropriate for school. And here, let me draw these triangles. And if these two angles are the same, then if this side is the same, or this side is the same, or this side is the same, we will have a congruent triangle. Just as long as that side that's the same is positioned similarly to the location of those angles that we know. The last rule, rule 4, is where right angle triangles have the same size hypotenuse and one of the other sides are the same length. And that would look something like this. While we didn't cover this in GeoGebra, by using the sort of trigonometry that you would have learnt last year, you should see that rule 4 is pretty much the same as rule 2. Okay, make sure you write down all those rules and keep them with you while we work through this exercise. And I'll see you in the next section. But before we get to that next section, you may wish to pause the video now and try the building understanding questions in the new book, which corresponds to questions 1 and 2 in the old book. In this section, we'll be analysing triangles to prove whether they are congruent or not. We'll be checking if angles or side lengths match. If they do satisfy one of the 4 sets of conditions, we declare that the two triangles are congruent to each other. Let's recall that the 4 conditions are SSS, where all sides are equal, SAS, where two corresponding sides and a corresponding angle are the same, and AAS, where two corresponding angles and one side is the same, and RHS, where we have a right angle with the hypotenuse and one of the other side lengths are the same. Note that this does not mean right-hand side. Okay, let's apply these in example 3, where we're going to prove that these following pairs of triangles are congruent. In part A, we have a triangle A, B, and C, and another triangle D, E, and F. The angle BAC is 80 degrees, and also the angle EDF is 80 degrees. Another fact is that the line AB is equal to the line DE, and the line AC is equal to the line DF. Therefore, we have two sides that are the same length and are connected by an angle of the same size. Not only do we have two sides and an angle the same, but they are in the same position around the triangle in relation to each other. So they're clearly corresponding to each other. So by SAS, ABC is congruent to DEF. All right, let's move on to part B with the triangles ABC and DEF. With these pairs of triangles, the angle ABC is equal to the angle DEF, and the angle ACB is equal to the angle DFE. In these angles, notice how the first point stays the same, whereas the other two swap order. Oh, look, I noticed I've made a mistake. That should be ACB. Perhaps I just wanted to say ACE. Anyhow, as I was saying, those first 2 points are the same, but the second 2 points switch order. So clearly these angles are corresponding. We also have the side length AB is equal to the side length DE. Now these side lengths are corresponding because they both of them connect to the angle marked X and not to the angle marked Y. So because we have two corresponding angles and a corresponding side length, we have AAS. Anyhow, ABC is congruent to DEF. Alright, that's the end of the example. Pause the video now and work on questions 1 and 2 in the new book and questions 3 in the old book. I think it'll be nice and easy if you methodically go through each angle and each side length. Anyhow, I'll see you in the next section. In this section, we're going to learn how to apply the conditions of congruence to find the properties of different things in other shapes. Recall in the last exercise, we used the fact that triangles are the most fundamental shape. In other words, each shape can be described as a collection of triangles. Remember the angle sums? Because when we know there's a congruent triangle in both of the shapes, we also know that all sides have a corresponding side of the same length and a corresponding angle of the same size. In this exercise, we get a taste of using this technique to explore two shapes. Pay close attention to master this skill because in the next exercise, we're going to use it to explore parallelograms. Okay, let's put this into action with example 4, where we have this diagram here with points A, B, C and D, and the angle DAB is equal to the angle DCB, and they're both equal to 90 degrees. Once again, notice how I've just used a box to say 90 degrees. Also, the side length AB is equal to the side length BC, and the side length AD is equal to 3 centimeters. In part A, we have to prove that the triangle ABC is congruent to the triangle BCD. We can see both triangles have a right angle, which is DAB and DCB, and both triangles share the line DB for their hypotenuse. Of course, we know DB is a hypotenuse because it's the side length that's opposite the 90 degrees. Now, because AB is equal to BC, they also have another side that is the same. So by the right-hand side rule, ABD is congruent to CBD. And that also reminds me I've made a mistake at the start. That should have been proved the triangle ABD is congruent to the triangle BCD. Let me copy that diagram because we'll need it in part B where we have to prove that AD is equal to CD. So this is pretty straightforward. We know that ABD is congruent to BCD and AB is equal to BC and BD is the side in both triangles. Then AD has to equal CD because all sides are the same length in a congruent triangle. Okay, that's clear, that's done. So let's move on to part C, where we're asked to find the length of CD. And let me scroll back down so we can see that diagram. Now from part B, we know that CD is equal to AD, and from the diagram, we know that AD is equal to 3 centimeters. So therefore, CD has to be equal to 3 centimeters. And that's it. So while part B and C were not too challenging, it's an example of what you can do if you first prove congruence. From that, you can extrapolate other properties of the triangles or shapes. Alright, at this point you should pause the video, question 5 in the new book, and question 6 in the old book. And you'll get to start to apply the skill we've learnt in this lesson that's going to help us explore a lot about geometry. Anyhow, I'll see you in the summary. To be successful in today's lesson, you will know the meaning of the term congruent, be able to match corresponding sides and angles in congruent figures, know the 4 tests for congruence in triangles, and know how to use the 4 tests to prove 2 triangles are congruent. And finally, be able to use congruence of a triangle to prove other properties. Okay, this is the first new information in this unit, and you'll be using this skill to discover properties of different shapes. Using one thing we know to be true to deduce some other truth is the most fundamental part of mathematics. It's also the most fun and interesting part. So, welcome to the journey that us humans have been on for thousands of years. This is how we've managed to develop medicine and travel to other planets. Hopefully your generation takes us to the stars and cures cancer. Of course, you're going to have to keep up the hard work, so we'll see you in class or the next video. See ya!